Hi guys, so what we're going to do today is we're going to start graphing some polynomials. And what we're going to do in order to graph our polynomial, we're going to look at a couple different components of the equation to draw a couple specific things. So the first thing that we're going to look at is end behavior. So in order to do our end behavior, this is going to tell us where does our graph start and where does our graph end. In order to figure out end behavior, what we're going to do is we're going to think about so we're going to look at two things in our equation. We're going to look at the degree of the polynomial, which we looked at yesterday when we talked about what polynomials were, and then we're going to look at the leading coefficient, and we're going to determine is it a positive or negative leading coefficient, and is the degree odd or even. So in order to remember what these look like, instead of memorizing them, it makes a lot more sense to think about a common function that you know that fits those characteristics. So for example, this first one here we're going to look at is an odd degree and a positive leading coefficient. Now if you remember from yesterday, an odd degree was when my equation was all FOILed out and all multiplied out, not in the factored form. I looked at the highest numbered exponent. If that exponent is an odd number, so for example, y equals x or y equals x cubed, those are both odd degree polynomials. They're also both positive leading coefficients, because in both cases my leading coefficient there is just a 1. So these are both examples. Now, all I care about here is the end behavior. So I need to think about what that graph looks like. I know y equals x looks like this, and I know y equals x cubed looks like this. In both cases, my ends, I have 1 here and 1 here. So what that means for me is that that's what my ends are going to look like when I draw my graph. And I think I just lost. Hopefully it's back now. Now what my graph does in the middle, whatever it does in here, it could connect straight, it could do something like that. We don't know what it's going to do. We're going to deal with that later when we talk about zeros and intercepts. For right now, we're just looking at the ends of my graph. Now what's important about the end behavior is this information that's listed at the bottom. It says, as x approaches infinity. So really what end behavior is describing, it helps us draw the graph, but it also helps us figure out, as my x goes towards infinity, what are my y's doing? This is going to be similar to what we do later on in the year with something called limits. So as my x's approach infinity, I need to figure out what my y's are doing. So as my x's are getting bigger and bigger and bigger, the y's are getting bigger as well, which means my y's are approaching positive infinity. Then as my x's approach negative infinity, which means as the x's keep moving that direction, my y's are getting smaller. So as my x's approach negative infinity, y is also approaching negative infinity. So that's the other way to describe our end behavior. So we'll do two things with it. We'll describe it with this limit formula. We'll also look at it for actually drawing our graphs. So another option is still an odd degree polynomial, but instead of a positive leading coefficient, I have a negative leading coefficient. So a negative leading coefficient would be, an easy equation to think about would be like y equals negative x. So if you think about y equals negative x, you guys all know what that looks like. It's a straight line with one end here, the other end is here. So my ends are going to look similar to that. I'm going to go up to the left and down to the right. Now again, in terms of any negative odd polynomial here, my graph can do any sorts of numbers of things in the middle, but I know my ends are going to go in this direction. So if I look at that picture, as my x's approach infinity, this time my y's aren't getting bigger, my y's are actually getting smaller. So as x approaches infinity, y is approaching negative infinity. Same thing on the left side, as x approaches negative infinity, this time my y's are getting bigger, because as those x's move smaller to the left, those y's are moving up towards the top. So y is approaching positive infinity. Alright, the other end behavior we're going to look at is an even degree polynomial. So an even degree polynomial with a positive leading coefficient, the easiest equation to think about that you know what it looks like would be something like y equals x squared. So y equals x squared, you know it looks like a parabola, but if it's positive, both ends are going up. And again, this graph can do anything in the middle. We know the regular parent function would look something like this, or if it's a higher degree even number, it could do terns and other things like that. Again, for right now, we're just worried about the ends. We'll deal with how to mark up the middle when we look at the other components of this graph. So looking at my ends here, as x approaches infinity, my y's are getting bigger, so my y's are approaching positive infinity. And then as my x's approach negative infinity, the y's are also getting bigger, so the y's are also approaching infinity there as well. So with an even degree polynomial, both arrows are pointing in the same direction, and x going toward positive and negative infinity are approaching the same y value. Then the last one is just an even degree with a negative leading coefficient. That would be something such as y equals negative x squared. And again, you guys know it's going to end up where both arrows are in the same direction, but if it's negative, that flips it. So both of my ends would be pointing down. And looking at this graph, as my x's approach infinity, my y's are approaching negative infinity. And as my x's approach negative infinity, the y's are also approaching negative infinity. So this is end behavior. So when it comes to drawing our graph, the first thing we'll do is figure out the end behavior so we know where the graph starts and where the graph ends. Once we know that, though, we need to fill in the middle part of this graph. So in order to do that, we're going to look at three things. The first thing we're going to look at, second thing overall, clear shape with end behavior, is the y-intercept. Now y-intercept, you find this the exact same way you found it since Algebra 1. In order to find a y-intercept, you always plug in 0 for x. It's going to be the same thing with any type of function we work with. To find a y-intercept, you plug in 0 for x. Now you can find this in any equation. This is going to be easiest, though, if you have the non-factored form. Because if I have my non-factored equation, if I plug in 0 for x, then I'm going to get 0 minus 0 plus 0 minus 7. So my y-intercept on this equation would be 0, negative 7. So hopefully y-intercept isn't too difficult for you guys because we've been doing this for a while. Again, to get the y-intercept, you plug in 0 for x. Then the next thing we're going to find is the x-intercept. Now there could be multiple x-intercepts on our graph. There could be no x-intercepts on our graph. But in order to draw this, though, what we're going to do is we're going to use the factored form of our equation because that's the easiest way to find our zeros. You also can find zeros using things like the quadratic formula, but the graphs that we're going to deal with, a lot of them you're going to be able to factor and find your zeros that way. So if you take your polynomial and you factor it, in order to find the x-intercepts, which also, if you guys remember, have several names, those were also called roots, solutions, or also as zeros. In order to find those, what we do is we take each factor and set each factor equal to 0. So in this case, this is in my factored form, so my zeros here would be 0, 3, 2, and negative 7. That means that this graph for this polynomial would cross my x-axis in 4 places. It would cross at 0, 3, 2, and negative 7. So those are my x-intercepts. Now the part that's slightly new is going to be the behavior at those x-intercepts. So my graph isn't necessarily going to cross completely through it. The graph can do a couple different things at the 0. So the last thing we're going to look at in order to draw our graph is what's called the multiplicity of the 0. Okay, so what we're going to do is we're going to find the behavior of my graph at the x-intercept. And again, that's called the multiplicity. So if the multiplicity is equal to 1, my graph is going to cross the x-axis. Now what the multiplicity is, that is the exponent of the factor. Okay, it is the exponent of the factor. The exponent of my factor. So if the multiplicity is equal to 1, then my graph would cross. So for example, in the equation I had below, x plus 7, that had a multiplicity of 1 because that factor was raised to the first power. It doesn't have an exponent on it, but we know that means it's listed at the first power. So what that means is at the point of negative 7, my graph is going to cross through that point. If I'm starting from the left side, it would cross through that way. If I'm starting, if my end behavior is starting from the bottom. If my end behavior is starting from the top, it would cross through that way. But the point is that my graph is going to cross at that point. Okay, it crosses. If that multiplicity is an even number, so for example on the equation below, x minus 2 to the 4th power, that's an even number. If I had something like x plus 3 to the 6th power, or to the 2nd power, or any even number, then at that 0, my graph is going to touch the x-axis and then go back in the same direction. So for example, x minus 2 to the 4th power, at 2, my graph is going to touch that point and come back. So if it's coming from the top, it would touch it and then bounce back up in that same direction. If it was coming from the bottom, it would touch it and go back down in the same direction. So we're looking at what's happening at that point. So at the 0 of 2, because the multiplicity is 4, my graph is going to touch. Then the last option is very similar to the first. If the multiplicity is any odd number other than 1, so if it's 3, 5, 7, 9, the graph is going to wiggle at that point. What that means, it's going to look very similar. If I look at the function y equals x cubed. Y equals x cubed, the 0 has a multiplicity of 3 because the factor x is raised to the 3rd power. And if you know what the parent function looks like, it looks something like that. What your graph is doing there, that's what we're referring to as a wiggle. It crosses through, but it kind of crosses in a curved type of way. We're still going through that point, but it's not quite looking the same. But again, it is still going through it. Okay, so that's what we refer to as wiggling. And again, it's at the 0, that factor specifically. So x is actually a factor. It's a 0 of 0. Okay, so what we're going to do is we're going to combine all of that together to actually draw this next graph. So this next graph, we already figured out my zeros. Our zeros are 0, 3, 2, and -7. Those are the x-intercepts. Okay, those are my x-intercepts. Let me write that on the other side so it's easier to see. So I know my graph is going to touch the x-axis at least at those points. Then what I'm going to do is I'm going to figure out the multiplicity of each of those zeros. So at 0, the multiplicity is 1 because the exponent of that 0 is 1. So since the multiplicity is 1, that means that that 0 is going to cross. At 0, my graph is going to cross through that point. Then I look at the next 0. At 3, I have a multiplicity of 3, which is an odd number, so my graph is going to wiggle at that point. Then my next one is 2. At 2, the multiplicity is 4, and 4 is an even number, so the graph is going to touch at that point. And then the last one, the multiplicity is 1, so the graph is going to cross at that point. So what I'm going to do is I'm going to go ahead and label my x-intercepts. So I have -7, 0, 2, and 3. So in order to draw this graph, I need to find the end behavior first. So if I look at the overall degree of this function, the overall degree, remember, if it's factored out, I need to add up these multiplicities as if it were multiplied and FOILed completely out. So I have 1 plus 3 is 4, 8, and 9. So this is an odd polynomial, odd degree. And the leading coefficient, none of these x's have a negative in front, so this is a positive odd polynomial. If it's positive and odd, the end behavior is going to match a positive odd function such as y equals x. So one end will be here, and one end will be here. And then I'm just going to fill in the middle based on the information I have from my zeros. So -7 is the first 0 that I'm going to hit. At -7, my graph is going to cross. So I'm going to go cross through -7. Then my next 0 is 0. At 0, my graph is also going to cross. So I cross through 0. Then my next 0 is 2. At 2, my graph is going to touch. So I touch the graph at 2, and then I bounce back. And then the last one is 3. At 3, that graph is going to wiggle. So this one's a little hard to draw. I didn't really leave myself in much space. Let me scoot that down a little bit, just so you can see it a little more clearly. And this doesn't have to be perfect, just so you guys understand kind of the difference here. So it's going to kind of curve towards it. And that's my graph. Now, in terms of the heights of these points here, don't worry about those when it comes to sketching a graph. We're going to use our calculators later on to determine exactly what those points are. But when it comes to just sketching these graphs, it's okay to not know those exactly. All right, so I want to look at the first question off of your assignment for tomorrow. So what we're going to do is we're going to take a function, and the first thing we're going to look at is the end behavior. Then we're going to come up with the zeros, and then we're going to draw the graph. So we're going to combine all of these things together. So the first thing we're going to do is end behavior. So in order to determine end behavior, we need to figure out, is this function positive or negative? And is this degree odd or even? So in this case, that first number, there's no negatives in front of any of my x's or the leading coefficient. So this is going to be a positive polynomial. And this is not in its factored form. Okay, this is in the factored form. Since it's factored out, I need to add up those multiplicities to find the degree. So I have 2, and then I have 1, and then I have 1. So I have a total of 4. If this were to be fully multiplied out, the highest powered term would be 2x to the 4th. So since 4 is an even number, this is positive and even. Since it's positive and even, the ends of my graph are going to look like this. They're going to both be going up. So the next thing I do is I find the zeros. So the zeros of my graph are -1, 3, and -5. And then I'm going to find the behavior at those zeros. So at -1, because the multiplicity is 2, the graph is going to touch. At 3, because the multiplicity is 1, my graph is going to cross. And then at -5, my graph is also going to cross. And then all I'm going to do is draw my graph. The only other thing you could add to make this graph a little bit more accurate is your y-intercept. So for the sake of this little chart, don't worry too much about your y-intercept. Whenever we do the rest of the assignment, the other side, that will include the y-intercept on it. So I'm going to go ahead and mark my x-intercepts. I've got -5, -1, and 3. I know my ends are going to be up. And then I just follow the behavior. At -5, my graph crosses. At -1, my graph touches. And at 3, my graph crosses. So my graph will look something like this. All right, we'll look at the rest of these tomorrow in class. But hopefully, a lot of this is review. I think the only thing that might be a little bit new is your end behavior and multiplicities.